Hello and welcome to this session on Oracle Machine Learning Office Hours. Today we're going to be talking about Machine Learning 101 classification with Marcos Arancibia. My name is Mark Hornick. I'm with the Oracle Machine Learning Product Management. For today's agenda, we are going to first talk about the next session that's coming up, some submitted questions, and then our speaker Marcos will take us through an introduction to classification, and as usual follow up with question and answer after that. So the next session is going to be June 9th, and the topic is going to be regression. So very similar to the format that you'll hear today on classification, we're going to see about how to set up a data set for a regression modeling, build machine learning models that predict numeric values such as home prices, and evaluate model quality. So we'll look forward to that in the June timeframe. As far as the web questions, this was a really interesting one that came in, and they wanted to know how to identify and reduce biased data. Is there any standard technique available in Oracle Machine Learning notebooks using AutoML for SQL? Lots of people are discussing algorithms, but no one's really focusing on the preparation of test data and training data. Definitely, these are important topics, and I think this is something we can do in the future and focus just on these areas. But they'd like to know, how do you split data without any bias, and can we have some dedicated office hours to support this and talk about proven sampling and bias techniques? Well, we can't cover everything here to answer this question, but we can at least give you a few responses to this. You know, some people might wonder, well, what is bias in data? What are the different types of bias that we might have? One has to do with sample or selection bias. And this is where the distribution of values that you have in your data set doesn't actually reflect the actual population. How could this happen? Well, you might say we've collected data at different times of the day, month, or year. Just consider temperature values. If you always collected temperatures in the morning, that's not going to be representative of what you would encounter throughout the day. Or perhaps data was taken from a non-representative population. If you want to understand opinions of people across a given country, you wouldn't focus on just sampling people in one city. Also, not randomly sampling the data that you have. If you grab the first 1,000 or million rows out of a sequential file, you may have records that were entered earlier in the data collection cycle, and that might not be representative of what came later. Also, if you do sampling that omits representative cases, then you are also going to bias the data. Now, OML provides a variety of ways to sample data. And a few years ago, I did a multi-part blog series entitled To Sample or Not to Sample, which you might find useful, and we'll provide links to that on the OML Office Hours page. It was largely SQL-based, and that was what the question was: how do we use OML for SQL to address that? So you should find that that blog series helpful to answer these questions. But there are some other types of bias, outliers. If you have extreme values that are outside of the normal range, for example, if you have a few centenarians, people over 100, or billionaires, well, clearly those are going to pull the data in one direction or the other, and the model isn't going to work as well for that. There are other more subtle things, perhaps as confounding variables, where you have one or more variables that influence a predictor or target and can cause inaccuracies among the inferences that the model is making. And so this is where you see this phrase of correlation doesn't imply causation. You might look at temperatures and say, well, when the temperature goes up, we also get more shark attacks. Well, there's something that's tied in there that the temperatures cause people to go to the beach. So you have more people at the beach, and therefore that's implying that shark attacks might be increased. So you have to look for those types of things to not introduce bias into your models. And of course, the last one I'll list here, but there are certainly others, confirmation bias, where you have intentional or even unintentional manipulation of data to whether you include or exclude certain data that might help prove a preconceived position or hypothesis. So these are all things to be aware of with that. Now, there are a number of sort of manual data preparation tasks that one can take. outlier detection, binning, standardization, normalization, recoding. And just in the case of looking at how we can automate some of these things, Oracle Machine Learning provides automatic data preparation, where we'll automatically perform certain transformations required by each algorithm. So supported transformations like standardization, fitting a range, or sometimes called normalization, between 0 and 1, often necessary for a neural network or support vector machine algorithms. Binning of data, where you take a continuous numeric value and you want to chop it up into separate bins to turn it into what we call a categorical variable. Missing value treatment. How do we deal with missing values in our data set? Do we replace them with the mean, the mode, or some other imputation technique? And outlier treatment is another, where we look at how we might actually get rid of data points or adjust data points that reflect centenarians or billionaires or others. But sometimes you don't want automatic data preparation. You want to actually control this yourself. And if you'd like, there's also a package that is provided, DBMS Data Mining Transform. And that has a variety of functions, one of which is outlier treatment. We talked about that now. And it has techniques for Windsorizing, which is this notion of setting outliers to the nearest value that is not an outlier, or trimming, whereas you just cut off the outliers and you replace them with null and treat them as missing values. But one point I should make about auto data preparation is that what's also nice about this element is these transformations are actually embedded in the model. And these are automatically applied during scoring, so you don't even have to think about them. But if you're doing your data preparation manually, of course, you'll have to make sure that those get factored into the data that you'll be scoring as well. This last slide just shows you how you might go about leveraging auto data preparation. So in the case of SQL, you see that we're using the create model 2 function, and we have this vSetList variable setting prep auto to on. And that's all that's necessary to take into account, have the system take into account the transformations necessary for the given algorithm that you're working with. And the same feature is available also in the Python and our APIs. So if you'd like to learn more product information on Oracle Machine Learning, you can go to oracle.com/machine-learning. And there are a lot of links there and materials that you may find useful in your efforts to take greater advantage of the Oracle Machine Learning, both in the database and big data. There's also the always free cloud tier. If you'd like to start working with Oracle Machine Learning notebooks and the Oracle Machine Learning for SQL, you can get a free account here and create your own pluggable database, or PDB, and try out the features we'll be talking about. So with that, our session today is Machine Learning 101 classification with Marcos Arancibia. And without further ado, I will turn it over to him. Marcos, thank you for this session today.
Thank you very much, Mark. That's excellent. So hello, everyone. So basically, the idea today was to talk about a few things, right? Perhaps basic for some of you, but the idea is that we can start this journey on machine learning, and then we can go deeper as time permits as well. And if not, we can create another session. So the idea, again, topics are: what is machine learning exactly, and the classification side of it. Look into a little bit of the business problems that machine learning actually tackles. Understand the type of data that it needs, a little bit of the terminology, data preparation that Mark actually alluded with automatic data preparation, but also go into model evaluation, right, and AutoML as well. So basically, when you think about machine learning in general, right, there are many definitions, but typically we're talking about all of the field that can be multidisciplinary usually, right, where you have statistics, typical statistics, but then many algorithms coming from computational, from engineering. You have a lot of different fields that actually end up representing what machine learning is, right? But as an overall, we see it as a subset of statistics and then a subset of artificial intelligence at the next layer, where you will have algorithms that actually learn, right? They learn behaviors. They learn learn to predict, right, behaviors into the future. So deep learning, which is something you probably hear a lot as well nowadays, is a subset of what machine learning is, right? So deep learning is usually more on the, of cognitive, right, image recognition, text and sound and voice and things along those lines, right? But machine learning stays still as a wider part of that process. So there is a very famous CRISP DM, right, methodology, and that was created a while ago by many companies, and then it became part of SPSS, then became part of what IBM was working with it. But in general, the CRISP-DM method or methodology makes a lot of sense, which is the first thing you will do is have a business understanding of what you're trying to achieve with machine learning. And that goes back to data understanding. So do you have the right data that you need, right? And that can go back and forth because maybe you don't have the data that you actually require to understand and to try to predict that behavior. After that, you have a data preparation, right? So you need to work on that data preparation, and then you will go to modeling. Many times that go back and forth again because the modeling might not be, achieving what you expected. If you get to that point, then you will go to the model evaluation and then finally to deployment, right? So again, the evaluation will be the last thing you would do before deployment. If the model is really not good, things might have changed since you started working on that. People's behavior might have changed. So at that point, your model is no longer good and you just have to start over, right? So there are basically several components that make that. And, at the end of the day, when you think about classification, specifically when you think about machine learning, we're trying to work with algorithms that would help you identify things and components and people and behavior, right? So a few examples of those are classify cells as cancerous or benign, right? Tumors. Using data from coming typically from medical devices and patient information and whatever you can grab, right? X-rays and MRIs and different types of measurements. And we're actually going to see a few examples of that specific type of example of problem, right? That on a demo. Then I have the famous identify a transaction, right? Is it a fraud or is not fraud? So the kinds of things that go into that would probably be based on, customer behavior, right? Have the guy ever purchased something here? Location of the transaction, right? So Marcus is in Miami, and now suddenly there is a swipe of the credit card, in Utah, right? So what's going on? Time of the day and day of the week, right? So do I ever buy something at 2 a.m, right? Ever? Distance to my home, right? So maybe there's a transaction happening at 300 miles from my home. That might not make sense, right? Distance to the last transaction. So I had a transaction over here, and in 5 minutes I have a transaction, physical transaction 100 miles from here. It doesn't make sense. So again, there are many things that you can think of, and these are all the domain knowledge and expertise that you're going to bring to the problem, right? Where you can actually create these variables or find information about these variables, right? Also predict if a customer is going to buy or not a product, right? This is typical. So you look for past customer purchase behaviors. You look for other people's behaviors that are similar to this customer. You look for previous marketing campaigns, right? Website visits, links and clicks, and all of those things, right? And finally, these also apply to machines, right? So machines are all the time working, measuring, spilling out logs, right? And you really want to know whether a machine is going to fail soon or not, right? And there are many, many cases, and good cases for oil companies, right? They have to drill, and the drill bits will break, and it takes them 24 hours to replace a drill bit. So how can I help that personnel working, right, to understand that this drill bit is about to break, right? There's a high likelihood that this thing is going to break and it's going to need replacement. So you better go and fetch already a replacement instead of wasting a 24-hour shift, right? So those are many of the things that classification would do. Now, what is the type of data that you need then for classification, right? So typically, let's say I'm trying to predict if a customer is going to buy or not a product. You need historical data, right? So the idea is you need historical data from previous customers, from other customers, or from this same customer, for example, if a product is similar. But the idea is you have data from all your customers already. So what you want to do is you want to say, okay, let me look at all their information and then see whether they purchase or not this product, right? And that's the way that I can use that information to help me predict the future behavior, okay? Now, with that data, right, the problem is you have to realize when new data is coming, I'm not going to have that purchase or not purchase, right? I'm the one that have to say whether a customer is going to purchase or not. So when the new data comes in, you're actually going to have a decision, right? A model has to decide whether he thinks that the customer is going to purchase or not, and what's the probability of that purchase, right? Typically, the models will give you that likelihood or probability that this is going to happen, right? So at that point, then what we're looking at is those two components, right? So we're looking at whether a customer has the likelihood or what is the most likely outcome that the model decided, right? Yes or no, and the likelihood, right? The probability there. So several names are used, right, for different components depending on the study, right, on the field that you're looking at. So when you think about things like these components, right? So this, let's say this part of that. So the chunk, right, of the data in the middle here, you would call these chunk normally table columns, right? But people can call it, variables, attributes, fields, or predictors, right? So it really depends on who you're talking to. If you're talking to a data scientist, if you're talking to someone that is a statistician, right, he would call it a variable easily. But if you're talking to IT, that will be a column, right? So it really depends on who you're talking to, but normally that might have many names. There's also a column on the table that normally you would use as your case ID or unique ID. That is very useful to have a customer ID of sorts, right? In many times it does not, many companies do not store or do not allow the data scientists to work with things like social security numbers, right, for security reasons, or their full address or things like that that might be unique. So normally you would have to create your own, or you would work with the database and get an ID for you, right, for your work. And then on the right-hand side, you have the table column here, a target, right? So what to predict, right? So that is what you're looking for. Is it purchase? Is it broken? Is it fraud? Whatever it is, normally there's a column there that has that class, right? And then the classification algorithm will try to recreate this thing, right? Looking at the behaviors here. And finally, the row, right? So you have a row on a database table, you have a record, or you have a case for statisticians, right? Or an instance as well, or an example, right? So these have, again, many names, right? And finally, the data, right? In terms of the data, it can be, of course, a database table or view, but it's called, data set as well. You can call it a training data when you need to build a model. You can call it a test data to evaluate a model, right? So those are the different names that you might find. But what about the other ones, right? What about these guys, right? So in terms of specific columns here, normally the columns that the algorithms are spitting out as a prediction and as the likelihood would be called a prediction column and a prediction probability column, right? Typically. So, and that table, right, is usually again, another database or typically the scoring, right? So normally you will actually receive new data. You will not have that purchase or not purchase, behavior, but you have to then classify and work with that algorithm to estimate that. So that's basically what we would call the scoring data. Now, data preparation is something, as I was mentioning before, important and critical. And but perhaps one of the most important things for all algorithms, right? It doesn't matter which algorithm, is going to be to split the data into training and tests, right? And validations. So what happens here is, you need to build two sets based on random samples of the original data set. What you want to do is you want to split that original data into a training and test data. And then you want to build your algorithm and make your model build the algorithm on the training data, and then test the quality of the model on your test data. You want to make sure that, and most of the time, right, they can be a separate, distinct set, right? There are many other techniques and advanced techniques and k-fold, so that you can use to split and create more splits when you don't have enough data sets or enough records, right, to work with. But normally, out there in real life, you would see enough data where you can actually just split that into two sets. You build that model on the top side, and you keep the test data aside, right? You keep it on the side here. Now, the idea with that is you'll keep it on the side, and after the model is built, you will then pass the data to the model without the target. So you keep the actual response for yourself, just pass the data to the model, because the model is going to look at the data, and then the model is going to have a prediction. The model itself is going to say, oh, looking at this data based on the model that I just built, I predict that this is going to happen. Now, after you do that prediction, comes the good part on the right-hand side, where you're actually going to compare the model prediction with the actual known responses. You now can, without having to load new data coming from, from anywhere else, you can actually just test now. What would the model say? What would the model do based on the data that you're looking at right now? And you can compare that with that confusion matrix, right? So you can compare the target with the actual responses and create something that we call a confusion matrix. I'm going to talk about the confusion matrix in a second. But that's basically how mechanically you go by getting to that point where you can now create that process. So also another very important component of data preparation, right, is perhaps data transformation, right? So there are many transformations that you normally would do, but standardization, missing value, so all of those things you have to take into account. Mark was saying before that the automatic data preparation takes care of that, so I'm going to briefly click on that as well. But there is one key thing here, is that you have to realize that when the data comes in, that basic information you have normally has a lot more power than what you think. The data itself, the raw data coming, for example, a date, right? So just as an illustration, that's today's date, right? So I got 5/19/2020. But what does that mean if I have that on a customer side, right? On a customer data set. So the idea that I'm looking at here is now I can think about the basic information, like, how long, if I take a date, right, and just that number, how long it's been since, the beginning of the year, right? How many days? I know that today is a Tuesday. I know that this is a third day of the week. and I know it's the second day of the work week. I also know that I have a sunrise and sunset, right, times of that day. I might have the weather of that day, right? Today is overcast if I look outside here. There were flood warnings in Miami, right? So why would you think all of those things are important? Well, think about insurance, right? Think about a car insurance company trying to see if an accident happened in that day. They will take the time that the accident happened and they start looking. Was it night, or was it, was there enough light outside, right? Was it raining? Was it wet? How was the weather? Were there floods in the city, right? So all of those things are important depending on the type of company or that you're, or the data set that you're working on, just by looking at one single date, right? So one single point in time. So that is important. Now, that is just basic information, right? On the other side, we have domain knowledge as well. So that date might be, how many years this customer has been a customer of mine, right? How many days has this machine been operating, right, since it started? How much, have a customer increased their spending with me in the last 3 months, right? So then I can do that average of the previous 3 months because I now know what are the previous 3 months, right? Or how much the revenue last month have declined compared to the average of the previous 3 months, right, before that. So now I am able to look at the month, the days, compare that process, right, and understand the decline or increase in spending, right, from a customer. And how much the customer has declined usage, for example, since my last offer, right? Or how many months it's been since anyone contacted the customer. So there is a lot that can be derived, again, just by looking at a single record, right, coming from that customer. So it is very important for us to pay attention and work on that process, right? So as Mark talked about already before, right, data preparation is important. Oracle Machine Learning includes data preparation. It does, and I'll leave the slides here with more details for you guys. Mark's slides were more succinct. These are longer explanations, but basically, this is part of what the data preparation that Oracle Machine Learning brings that normally you would have to pay attention to, right? So binning and discretization, normalization of columns, outlier treatments, right? So outliers is, I always remember of a credit scoring company that I was working with, and they had I think they had 8 customers that were listed with their credit limits was over, I think, $500,000. So that was definitely not normal, not your average consumer in that database, right? Because the entire set of the rest of the database had limits that were below, 50,000 or something like that. So one thing is important is you can remove that data, but usually what you want to do is you want to explain why, right? So we went back to the team and talked to them, and yes, those were the 8, owners and VPs of the company, right? So of the bank. So yeah, that makes sense, but then you remove them because they're not your typical behavior, right? You don't want to have that kind of behavior mixed with all the rest of your data. So those are things that you want to do, right? Now, specifically back to the model evaluation now and the confusion matrix, right? So the confusion matrix is something very simple to build, right? So basically, remember when we were talking about, I have the algorithm that tells me that something was happening, and the actuals, right? Which is, this is actually what happened. So basically, when you look at something like this, and these will come in many forms, okay? When you look at the confusion matrices, you will see actuals on the top and predicted on the side, or you would see the other way around, or you would see different zeros and ones in different positions. So that is normal, right? But that doesn't change. The numbers are the same. So what this means is these were the actual responses, right, found on the test data. So I had 30 responders here that says that was, yes or one for that. And I had 62 with no's, right, with zeros. Now, this is what my model predicted, right? So I was predicting, and my model predicted 20 over here, but then, instead of the 30 correct, right, my model predicted actually 32 in total, but only 20 that were correct. These 12 guys here were wrong. My model was predicting that it was yes, but this was no, okay? So that is one problem that I find on my data set, right? The other one is my model predicted this was a no, right? 60 records here. My model predicted this was a no, but this guy was an actual responder, yes. Okay. So the correct then, the correct cells here, right, are the 1, 1 and the 0, 0, right? I predicted this was a bad customer or no non-buyer, and they were a non-buyer. So I got 50 over here. So normally what you want to see is these diagonal here increase in size and get very big, and hopefully this diagonal over here of the errors get lower and lower in number as you try to perform a better and better and more advanced model. That is typically what you would like to see. So in this case, I'll give you just two simple definitions: precision, okay, and accuracy. And these are critically different things. So in machine learning, precision really takes into account the true positives versus all the predictive positives. So this guy, precision, is only looking at, hey, I predicted 32 were going to buy. Out of those 32, 20 did buy, right? So I'm good. I'm 62.5%, so not great, but I got, my result, right? Now, the problem with precision only is that you're not caring about anything that happens with this, right? So if you only use precision and you keep on working on just a precision of models, you might end up with a model that is actually able to predict well when you have a customer that's going to buy, but you might be filling this guy down here up with a lot of customers that you are predicting they would not buy, but they would buy. So you might be leaving a lot of money on the table, right? Because you're trying to optimize this proportion over here on top. So again, it's all a matter of cost at that point. So there are techniques that would allow you to add a cost matrix, and actually Oracle Machine Learning does have that. So once you have that kind of matrix of cost, you can say, you know what, this is valuable, but this might be very worrisome for me because I am contacting, right? I might not be contacting these guys, but these guys would be my great customers, and I'm losing a lot of money because this guy's getting bigger and bigger and bigger, right? So on the precision side, I'm improving my precision because I'm trying to say, okay, you know what? When I contact them, I want to make sure that everyone is a buyer. I don't want to waste my time with people that are not going to buy. That's fine. But think about it the other way. Think about a fraud problem. In the fraud problem, you want to be able to identify the fraud. But if you leave this guy underneath increase too much, these are frauds that you're not detecting and you're letting go, right? You're letting this thing run. So it really depends on the problem, where you want to pay attention to, right? So again, precision is usually only looking at the top two numbers here. Accuracy, on the other hand, is actually taking into account the entire confusion matrix. So because of that, accuracy makes more sense when you're in general trying to just find a good model for your problem, and then you can drill down from there. So accuracy takes into account those two numbers, right? So not only the true positive, right, which is something you're going to hear a lot in machine learning, the true positive cases, which is this one, you predicted they were positive and they actually were. and the true negatives. You predicted these guys were not going to buy, and they didn't, right? In fact. So the true positives and true negatives, right, divided by the entire sum of the entire matrix is what actually gives you the accuracy, okay? So again, this is very, very useful, very much used to evaluate models. And I have a sample here from from Wikipedia. So if you guys take a look at Wikipedia, I would advise you guys to take a look at that. You have links that you can click and drill down into every single component here. So you see this is the confusion matrix, but then you have all of these different types of statistics, right? So precision, and then you have positive likelihood ratios and false positive rates, true positive rates. So there are many, many things that can be computed here, right? And the famous type 1 error and type 2 error, right? So false negative versus a false positive, which might have a different cost, again, depending on your problem, right? If you're calling too many people and you're just bothering people that are not interested in your product, well, that might be marketing, so it's not hurting you too much. But if you're calling very important customers, trying to sell them something, customers might be bothered about it, and they might actually not buy from you anymore if you keep bothering them. So that might be something that you don't want to have too much, right? The famous false positive. You're thinking this guy's going to buy this. If you increase the false positive on fraud, it's bad as well, because now you're starting to deny transactions that were originally good, and you're denying those transactions a lot. So that is also going to be something that might be bad for you. Okay. And finally, there are many statistics that we normally like to use that could cover the entire process, right? So accuracy is one that will include everything. F1 score is another one that takes into account a very good chunk of the information you can extract from there. Okay. Now, before I go into the demo, I also want to talk about AutoML, right? So I'm going to finish my demo with AutoML, and I'm going to come back to this process. But basically, part of the Oracle Machine Learning for Python, right? We're going to have this AutoML component that's going to have auto model selection, auto feature selection, and auto tune. You guys can go back to our session on Oracle Machine Learning from January this year, where we have all the details about it. Okay, so I'll switch into now my my browser, and hopefully you guys can see my screen. So basically, the idea is on this session, I'm using the Oracle Machine Learning for Python, and I'm going to look into, again, classification, right, that we were talking about. I'm going to use a specific data set, right? So there are some data sets that come with Python scikit-learn, and one of them is the breast cancer, right, from the University of Wisconsin. So they had some features that were computed from a digitized image of a fine needle aspirate from a breast mass. And the original data set contains 31 attributes, including a target attribute, which is 1 for malignant and 0 for benign. So for this very simple example, I wanted to show you guys something that was intuitive, right? So instead of using all these columns and attributes, I'm going to use just 2 attributes to show that in 2D, right? So I have there, an initialization of my environment. That's basically something you might not need on Autonomous Database. You're going to have that already done for you, right? Not needed as well to connect to the database. But what I'm doing here is I'm loading the data set from scikit-learn, right? So there's a data set on scikit-learn that it has the breast cancer data. So I'm loading that data and creating 2 separate pandas data frames, right? One with the target, one with the predictors. And then I push that into a database table, right? So for us, from Python, I can just say, drop table, and right with a try, so that if there's any problems, it just continues. So I delete any previously existing table on my database that's called breast cancer, and now I create that with an OML create, I push that concatenation of the X and Y's, right, of that pandas data frame as a breast cancer. So if I want to take a look at the statistics, for example, right, from all columns, now because this breast cancer like that is not only the table, right, but now this guy is actually our pointer, right, our proxy. So I can use like things like .describe in Python, right, against that table proxy, and this guy will run exactly like it is running inside Python, right? So naturally the same way. So I get all the statistics, things like the counts, the standard deviation, minimum, maximum of each of the columns, and I can see the names of all of the columns here, right? And at the end, at the rightmost, I have the target column here, right? So if I wanted to take a look at the data set itself, again, I can just do a Z-show on it, right? And then you get the entire data set to take a look at. Now, this is the raw data, right? The other one was statistics. This is actually the raw data, just so I have an idea of how do the columns look like, right? All right, now, the first thing I want to do here, because if I created a chart with all the data points, things are going to look kind of not nice in the screen. I wanted to create a sample, a 40% sample, right? So in Python, I can just create a sample using my proxy, right? And right now I'm running with this poll, but you don't need that, right? That when we release OML for Pi in autonomous, the sample is going to be already running for it. But right now, what I'm doing in this little environment of mine, I'm pulling the data, doing the sample, and then I'm pushing it back to the database, right? I'm creating a second table on the database with a second proxy that is a 40% sampling out of that. Also in autonomous, of course, you can do something easier, right? So you would be able to do just create a new table, right? As select sample 40, and then you'll be able to sync a new table as well with that same name, right? So these are two options on how to get a 40% sample of that data. Again, this is random sample. There is an entire section that we can spend talking just about sampling and stratified sampling and the correct sampling and oversampling that normally goes with machine learning. So I think we're going to dedicate a session for data preparation and for sampling and all of that. So we're going to use two columns for the project. Mean symmetry is a measure of symmetry of the tumor mass, and concavity. And the binary target, right? It's a column that is included. So I have these three guys here. I have a malignant tumor or a benign tumor, right? So if you can use for sure Zeppelin visualization, right? That's up to you. You can play with it and look at, the points and the distribution and get, the 0 and 1s like that, right? So Zeppelin has this built in. But I rather use, for example, something out of Python, right? So MatPlot Lib that we will make available as well with OML for Pi. So this looks a little, in my humble opinion, a little better, right, for us to visualize the data and understand the zeros and ones, right? These are the things we're trying to predict. So if you look at this, the distribution in concavity and symmetry, you have, the malignant tumors are actually crossing the boundaries, right? So you have a few ones that are actually way in the middle of the others, right? So even though these are the benigns, you have benign tumors that are very much similar to the malignant ones, and you have malignant ones in the middle of others that look like benign. So it is typically a problem that you'll find everywhere. It's very rare that you will find a problem that has a complete separation, okay? Now, again, remember we have 31 attributes, original attributes, and those 31 original attributes would probably give you a better separation if you mine all of them, right? And if you do this in 3D and 4D and 5D, and you start evaluating all at the same time. Right now, we're looking at 2 dimensions only because I want you guys to have an idea for visualization. So basic splitting. Remember the split, the famous 60-40 or the splitting that we were doing. We're doing a split here, right? And right now, then, after I do that split, I'm doing the split again on top of the original proxy, right, for my sample in the database. So I can use split directly on Python, but this is happening inside the database, right? So again, everything here is staying in the database. And I can see the shape. So the original data was 228 records, 31 columns. I have a train that has 142 and a test with 86 records. On the right-hand side, then, what I'm plotting here is I'm saying, okay, what if I wanted to have an intuition, right? Say you want to run a query, and you think your query can help you, and you have a person with an intuition, a doctor, or someone that has an intuition, and said, you know what? To identify malignant, right, with a high likelihood, I think you should cut that plane right there, right? So I think that the mean concavity, right, at 0.7 or 0.07 makes sense to me. So what we can do with that information is, sure, it's a classification, what I call a gut feeling, right? So your gut feeling is telling you, this is what I think is going to work well, right? Now remember, this is the training data set that I'm looking at, right? What I now will do is I'll take your gut feeling and process that into the test data set and tell you, surrounding in black, the dots that you said that were supposed to be malignant. And you can see that by your intuition, you still ended up selecting a few guys here that are benign, right? And they fell inside your area. But also, of course, you couldn't use all these other reds that were actually were perhaps not in here, right? You see, they're not. This guy is not there, right? Because this is only on the test set. So you couldn't see that before, right? You wouldn't have that intuition there. So we can run a confusion matrix, right? Very simple, and then we can run, print a confusion matrix with the true positive and true negatives, and then we get that very simple outcome here. So remember the diagonals, right? Even though this is different, right? I have a 1 over here and a 0 over there, but the diagonal is important, right? So I got 30 and 44 my diagonals. And this is just by intuition, which is fine. Now, the second very easy model to work on is decision trees. So decision trees are very simple models. We can build them very simply, again, with decision tree settings. We build the model, we fit the model against the trained data, and now I'm doing a prediction on the test data, right? And the decision tree also took more or less that approach, right? Because decision trees are very straightforward. They will decide where to cut. And they got an actual accuracy that was a little lower than your intuition before, right? You got 22 and 51 over here, but it got, it tried to get more customers, more samples here, right? But then ended up getting too many, right? So naive Bayes is another algorithm we have. And again, we will have to find more time to explain all the different algorithms to you guys as well. But this naive Bayes algorithm is very simple. It's really a frequency. It looks at frequency and tries to understand that. And you can see by the prediction on the right-hand side that it did an interesting job. It actually was capable of finding points outside of the straight line, right? It's going to find points outside of the normality here, but it didn't do a good job either, right? So it picked up too many green, right? Too many benign tumors at that point. Logistic regression is another model that actually works on the straight lines as well. So it will give you that kind of straight line feeling here. But this time, it was a decent model, right? In this case, 88%, right? It was able to capture a very interesting capability here. And if you add, you can you can make it very more complex. You can build a logistic regression with feature generations and feature selections, right? But the problem is then it gets so complex that in this case, it is actually saying that everyone is one, right? So it's actually getting the completely wrong picture of what's happening, right? But again, because we have only two, we only have two attributes, right? So I'm just leaving it out here because it exists, right? Random forest, another one that can get very complex. A simple 5 trees with depth 3, right? Then is a very small sample, 84% accuracy. But if you get a 1,000 trees with depth of 5, right? Again, you can then get a little more advanced modeling and go all up to 86% of that quality. Support vector machine as well is another type of model that you will go and work with a kernel. So the linear kernel, the default, is again going to be something close to a straight line. You see, it's not exactly a straight line. It's going to give you 86%, but you can play with a Gaussian kernel, and then it might be a little more flexible. But the problem is it's too flexible. So you see there's probably a curve happening here, and it went to 84% there. Finally, you can add a complexity factor to that SVM, and then you can play with that again to try to reduce that curvedness that it had before, but it's still not great in this particular problem, okay? And at the end of the day, neural networks as well. So model build on neural networks, they, depending on the simplicity, right? So one layer with 4 nodes, you get something like this, 82%. You add more complexity, 2 layers of network on the neural networks and 4 nodes, or 4 and 2, right? Nodes there. Then you get something like this with 87%, and then you can get 3 layers, right? 8, and 2. And the problem is then you went too far, right? You went too far and it went down in the quality, right? So at the end of the day, you can work your way on all the models and all the algorithms, or because we're bringing this now, right, with the tool for you, you can also use AutoML. So you'll be able to just say, AutoML, I want to do classification. I want to use accuracy as my score metric. I'm passing to that AutoML algorithm, I'm passing that to you, the 2 columns that I have, and I'm giving you my target. And I want to see give me the top 10 algorithms. Please show them into ranking. This guy is going to run in this environment and this algorithm. It took 26 seconds, right? But of course, depends on the size of your data and the complexity. But these are the models it gave me. It actually gave me a random forest that is 89% accuracy. So it's actually beating me, right? Playing with this thing, it's beating me easily out of all of that. And then I have an SVM Gaussian, neural networks 88, decision trees, logistic regression, GLM ridge regression, SVM linear, and things along those lines. So on that sense, we have also automatic feature selection. So now I can feed and take my top model, right, my RF model, my random forest, and I say, you know what, I'm going to feed you and let you play with the features that you can select out of these 2 that are important. And then when I run the model tuning of that model, right, then I can run the model tuning of my random forest, right, and pass it the reduced train, right, and then pass it the target. And finally, I'll get that model tuned, that random forest that basically finishes with, this best, algorithm, right, with 89% accuracy, right? And it was able to find things all the way out there, right, in different spots here. So it's a much more complex algorithm, but it's a simple version of that. So again, I just wanted to give you guys a quick highlight of all the algorithms, how they do, and what are the kinds of things they work on, and let you know that, of course, that capability is also going to come with the AutoML user interface. We're working on this. This guy is going to come after the AutoML components, but we're going to add that capability, right, of doing the things in the UI for you. So with that, we're at the top of the hour. We'd like to open to Q&A, and I apologize up front for the short time.
Okay. Well, thank you very much, Marcus. That was a great presentation. Really appreciate hearing about the details of classification. So are there any questions that anyone would like to pose? We did have a few on the Q&A. And so just to highlight what some of those were at this point, they wanted to know, was there any plan to release support for OML for Pi, OML for R, and AutoML for OML notebooks? And the response there is that OML for Pi with AutoML is coming soon to Autonomous Database with OML notebooks. And OML for R is planned for Autonomous Database and OML notebooks later this year. Another question was, is test and train split mostly based on the algorithm and data domain? I'd commented, Marcos, about 60-40 split is sort of typical, and depending on the distribution of the data, like for fraud, you might have very few positive cases, and so that could affect what you might want to do there for sampling as well as algorithm selection. Do you have anything you'd like to add to that, Marcos?
Yes, and I think, there are other cases where you want to do things like cross-validation, right? So if you have really, really few number of records, you might do cross-validation, which is actually you take the samples, right, of the training and test, and then you make the original training a test now, and then you use the data again, just to try to expose the model to the most amount of data possible, right? So I think that, again, that probably deserves an entire session dedicated to working on data transformation and creation of data sets, right? I think that's going to be something we can do. I see that you replied to the other questions, Mark. There are 10 new ones.
Oh, wow, we've got a lot of ones coming in.
So real quick, do we have a comparative of how our AutoML compares with Kera? I think it's Kera's, the package. I don't think we have, Mark, but I think it might be an interesting thing. It depends on what the usage is, right? For classification specifically, or we have for regression as well. But I think that's something we can work on for the future, to play with something along those lines, right?
Yep.
The machine learning on 19.3. Yeah, so machine learning, Oracle machine learning is available, right? So ever since release 11 or before. So the Oracle machine learning is available on your laptop if you have Enterprise Edition, for sure. You gotta check. There are a few things that can be installed in addition to that. The Oracle SQL Developer has the data miner interface that can help you. You would have to set up and install the Oracle machine learning for R by yourself. There are instructions on how to do that. The Oracle machine learning for Python, though, it's not yet available, right? And it's, as Mark said, is going to be available on Autonomous first. AutoML support algorithms on any specific algorithms. No, these are the AutoML supports the algorithms that I showed, the ones that are ours, right? The ones that are running in database for now. If you can get the Zeppelin notebook, yes. I mean, we're going to post it in our GitHub as soon as the Oracle Machine Learning for Pi is released. AutoML support for no, that was already. What else? How are hyperparameters tuned, right? Have any way to control what it's doing? Yes, there are a few things that you can invoke on the tuning and some options. Not a lot of tweaking, but yes, I think we have some options that you can use for that. And those will be in the instructions in the documentation when we release it. When we get the accuracy of the model, then how to get the accurate probability of the variables. Yeah, so depending on the model, I think what you're asking for is each of the influence of the variables, I imagine. So yeah, so there are models that will give you that influence that each variable has on the target, right, based on that model's behavior. So depending on the model, you can get that specific kind of things, and we have that ability as well. Does OML supports any deep learning? Yeah, not right now. These are probably longer term goals for the Oracle machine learning, but not at this second.
I mean, one of the comments we can make on that one is there is a capability that is coming soon. It's OML services, and it does do some cognitive image and text analysis, which leverages deep learning through pre-built models. And so you can look forward to hearing more about that in the months ahead.
Right. Will it be possible to locally run Oracle Machine Learning for Pi models? These that will have to be running against a database. So the models themselves would have to run on the database or on the Oracle Machine Learning services, as Mark mentioned. Right? They could be posted and deployed to that service, and then they will be able to run there as an API for you, or as a REST service, but not out of your laptop, unless you had a database server there with OML for Pi. And OML for Pi right now, the first release is on Autonomous only. Can we use any other frameworks like AutoGluon on OML? Not at this moment, but that doesn't mean you cannot do scripting right behind the scenes. So if you know what these AutoGluon would do, you could potentially script that in Python or script your PL SQL code behind the scenes and have it run for you something. So it will depend on APIs. How to get the probability, I guess, depending on the algorithm. So the algorithms will actually all give you probabilities mostly. Some of the GLMs will give you things like the log odds, right, of the variables, and they will give you the different than the what is the probability is, right? So you would need to do some transformations, but normally we allow you to actually ask for probabilities out of the models.
And one other thing to add to the probability question is that you can also get the set of probabilities if you are doing a multi-class classification, right? So you might want to know what is the probability of each of the possible predicted classes. And so that's something else that is available in the API.
Right. Sampling will depend on what you're modeling for sure. Yes, exactly. So sampling is very important. You got to be very careful what you're doing. If you're doing especially time series, right, you would probably want to get a portion of that series and then try to predict, a month in the future, a week in the future. That's the kind of thing you will do with these kinds of algorithms, right? You have to be careful and domain specific on these kinds of things. Updated OML for Pi documents, Mark?
Yeah, as far as the documentation, that gets released when the product is released. Certainly internally within Oracle, we have access to those. But as far as publishing those will only be published officially when the product is released.
Right. And then another one, the way Python was being used is that OML for Pi or something that could be done today. Yeah, so the idea is that you will have the Oracle Machine Learning for Python is really a module that will go on top of Python and then allow Python to interpret and work with database tables, right, and database vectors and database strings, just like they were a pandas data frame on Python. Not only that, you would execute algorithms, right, and the database will run the algorithms inside it. So you're running 1 million records, 10 billion records, that the autonomous database at that point is running it for you. You're getting the results, right, the model at the end of the day. So that's how we were doing it. I think that's what we're going to provide on autonomous, right? Can you use Oracle Apex for machine learning concepts? Sure. Oracle Apex is actually an excellent tool to build models. And actually, we have there is a whole session on office hours that our colleague Charlie Berger did together, I think with Tammy, on how to create an Oracle Apex application that was actually running machine learning behind the scenes and Oracle machine learning behind the scenes and running and getting scores right in real time. So that's a great session. Unsupervised learning and reinforcement learning in the future landscape. So we are going to actually do an unsupervised learning presentation, but on our case, what we're thinking is we have two types. We have one that will do the support vector machine, one class SVM that we call it, which will do anomaly detection, and the other ones are related to clustering. So those are the two types of things that we're going to do within supervised learning. But the reinforcement learning, again, is not still part of the product, right? So it is potentially future. It might come with Oracle microservices, maybe a few details in the future, but it's not yet here. If we can provide link to the recording, yes. All the previous recordings and this one will be accessible by one single link, right, Mark? I think
yes.
you have posted.
I've actually put the link in the Zoom webinar chat for folks because that question was asked over there as well, but we can make it available for you.
Right, so the link to the video is the same thing, and the link to the previous past recorded sessions. And I think that's it, Mark.
Great. Well, thanks again, Marcos, and thank you all for attending, and we look forward to seeing you at our next session. Until then, take care.
Thank you very much. Thank you, everyone.